Hi everyone, welcome to the last talk of the year. Um, Today our speaker is Maswelin, and he will be discussing converging advances to accelerate molecular simulation. Prof. Maswelin is a full professor and researcher in machine learning at the University of Amsterdam. He's also a distinguished scientist at MSR. Thank you so much, Prof. Maswelin, for accepting to speaking with us today, and looking forward to the talk. Before we jump into the talk, if you have any clarifying question during the talk, please raise your hand, and we just kind of let you ask the question. And if you have a question that need more discussion, please keep those to the end or add them in the chat, and we will be taking them at the end. Thank you again, Prof. Wallin, for doing this, and looking forward to it.
Thank you, Prudential, and also Cas for organizing this. It's wonderful to be here. So again, feel free to ask questions during the talk. I'm giving sort of a version of the talk I gave at NeurIPS. So in that sense, if you've already seen bits and pieces of it, I apologize. But sometimes it's good to hear things twice. But okay, so let me start the talk. So can everybody see this?
Yeah.
All right.
Yes.
Okay. I was hoping this would start rotating, but it doesn't really. Okay, but anyway, so I'm going to talk a little bit about AI4Science. And so the overview for today is I'm going to talk a bit about what we call the fifth paradigm of scientific discovery. Then I'll talk a bit about PDEs, the very exciting field. Many things are happening right now in that field. And then I'll talk about molecules. And so first a little bit of perhaps superfluous history. So around 2010 or so, I guess the first really big breakthrough of deep learning happened when a field which was stagnant for a long time in speech recognition, where HMMs ruled the day, but the error rates weren't coming down very much. At that point, Jeff Hinton and his lab started to apply deep learning to this problem, and the error rates started to drop again to the point where now it's a practical tool. You can talk to your phone, and your phone understands you more or less. And soon, it, of course, will also be able to talk back to you now that we have ChatGPT. So around 2012, something similar happened. There was a competition called ImageNet. Again, the lab of Jeff Hinton applied AlexNet, which was a deep neural net at that point. And so this team wasn't a computer vision team, but they applied this sort of deep learning technology, and the error rate sort of halved at that point. And from there on, you can see here that the error rate kept going down to the point that at this point, it's almost sort of at human error, although the errors are quite a bit different than the errors that humans make. So I thought this was an interesting one as well, which is in natural language models where a system was built that could explain a joke to you. So if you read the joke and you can't quite understand why it's funny, then in blue it's explained to you why it's funny, which I think in itself is quite funny, but it's interesting that a computer system can do that. And then of course there is this more recent image generation sort of technology where you provide a prompt, and then from the prompt it will just generate some image that expresses basically the text that you put in very creative ways. It sort of starts, it makes us rethink what creativity really means. And so that was also extended to video, and you can give a prompt and that will create a little bit of a video. And of course, most recently is ChatGPT, where you can just ask it a question, but you can ask it also to write an essay or something like that, or code something, or do some produce an Excel sheet or something. That it will all do that for you. And every time this happens, I keep being amazed of what's possible. So certainly 10 years ago, I wouldn't have predicted that this would happen in 10 years. And so even though sometimes people get impatient with self-driving cars, which always seem to be 10 years out, this type of technology really goes faster than I predicted. And it's really amazing what sort of these deep learning technologies can do for us in this field of image and video and language. But more recently, there is another trend, which I'm very excited about, which is to apply basically the same deep learning technology, and sometimes even almost literally the same, to a completely different field, like the natural sciences. So of course it started, or a highlight was AlphaFold, Deepmind's AlphaFold, where you give it a sequence of amino acids and it produces a three-dimensional structure of a protein, which is important for its function. Another highlight was, of course, the control of a plasma inside a tokamak, which is done using reinforcement learning. And I'll talk a little bit more about this application of generating molecules. And what is cool about this, I feel, is that it's exactly the same technology that's being used for images. So there's these diffusion-based generative models. And it's just amazing that the same technology generalizes between images, video, and then here also generating molecules. So the tool, the hammer I'll be using very briefly, I don't go into too many details, is this convolutional deep neural network. We'll probably know and love this thing. The basic sort of operation is this convolution, which is shifting a little bit of an image over, sort of a small little patch of an image over a bigger image, and taking the inner product between the pixel, the numbers sitting on the pixels of the image multiplied with the pixels sitting in your filter, and then adding everything up and pushing it through nonlinearity, and then creating sort of the representation at the next layer. So you can keep doing that for many different filters. So you get filter stacks. You can do downsampling to keep your memory a bit manageable. And then at the very end of that, you'll have some kind of more standard classifier to predict things. Now, the way I like to think about this is that this is sort of think of this as a message passing algorithm where, let's say, if you take a small patch of sort of a number of these pixels here in a square, each one of these pixels is sending a message to the central pixel, and it's most useful to think of the representation that's living on one of these pixels here as a vector, and then the components of the vector sort of cut through all of these feature maps here. And then each one multiplies that vector with a matrix, and then all these matrix vector multipliers are being added, including a message to yourself, and then put through a nonlinearity. Now, viewed this way, it's quite easy to then start thinking about a graph convolution, because this is, after all, just a very regular graph. The problem with the graph is that the nodes are, there could be, the ordering in the nodes is undefined, given that you just have the graph. And also the number of neighbors is variable. And so you need to do something. And the very simplest thing you can do is basically use the same matrix to multiply all the neighbors, which can be different from the one that you sent to yourself. In the beginning, people thought this is not powerful enough to do anything useful. Turns out it is actually very powerful already. But I should also say that many more extensions of this have been developed since then that are actually much more powerful. And so one of the more recent extensions is sort of a visualization here where we have spherical harmonics living on the nodes. And the nice thing about these sort of spherical harmonic representations is that if you rotate the neural network, it doesn't get confused about the fact that the numbers on its input now change. Because the thing is rotated. It understands that rotating things represent exactly the same physical system. And just for sort of further reading, and this is of course cherry picked. This is some work that we did, but there's a huge literature, I should say, here. So I kind of like this SE3 transformers. I can't say this is the best performing model, but it was the right thing to do at the right moment. In fact, it is being used, or a version of this is being used in these sort of protein folding algorithms, especially the one that's being used in Baker's lab, Rosetta Fold. I think Deepmind has its own version that's actually also called the SE3 transformer, but I think it's a slightly different architecture. And here's yet a different extension of this. I like this paper because it's sort of a unified view of all of these things. So if you want to start and sort of with a unified view, then that's a good paper to read. So the thing we've also been busy with and being excited about is symmetries. Of course, symmetries are extremely important in physics. And one of the two of the major examples are the fact that in sort of before the turn of the previous century, the electra and magnetism were considered two separate physical phenomena which had nothing to do with each other. But it turns out that you can transform one and the other using a observer that is has a certain speed relative to the other. That's called a Lorentz transformation. And so for one observer, you might see an electric field. An observer that moves with a certain speed sees a magnetic field. And so you can transform one and the other, and it sort of almost literally becomes two sides of the same coin. That's what we call a symmetry. And something very similar happened when Einstein thought hard about what gravity really is and how it could be distinguished from acceleration. It turns out you cannot really distinguish these two. So if you drop a ball in a gravitational field, or you drop a ball in a rocket that's accelerating, you can't really, if you don't have a window looking outside, you can't really distinguish these two things. And so he basically then claimed, oh, then they must be the same. And from that, all of that general relativity follows. And of course, there's also the standard model, which is the fundamental model of our elementary particles, which you can completely organize through sort of group theory and symmetry transformations, where particles transform into other particles using group transformations. Okay, so the tool that Taco Cohen started to sort of develop when he started his PhD thesis, around 2015, 2016, is the idea that you can use these symmetries inside your neural networks. So you can basically, acknowledge that under certain symmetries, the prediction should remain invariant. For instance, a class label, whether something is a gecko or not, should not depend on where you measure, the gecko or where the camera is pointing. And so that's of course just translation equivariance, and translation equivariance is one example of a symmetry. But you can generalize this, and this is a program that in my lab, MLab, we went through with many very excellent students. For instance, Maurice Weiler has been working also on these symmetries on manifolds. So if you have an egg, you can sort of rotate your egg, which is the symmetry of this manifold, rotation around the z-axis here. And then what you want is that if you filter and then rotate, or if you rotate and filter, things remain the same. Even more general is that if you want to do convolutions on manifolds like Möbius strips or spheres or any other manifold, you will actually need the same tools that you need for these equivariant neural networks. But now it becomes more like a local symmetry, and in physics that's called a gauge symmetry. So all this beautiful math that's being used in physics sort of maps one-to-one on a sort of deep learning technology, which I think is incredibly cool. Okay, so now I'll talk a little bit more about AI for science, and in particular in PDEs. So science spans like an enormous amount of spatiotemporal scales, right? So you can, study particle physics at picometer scale and femtosecond scale, all the way up to, astronomy at light year scale and giga-year time scale. And so all of these, but the beauty is that in all of these scales, physics is described by partial differential equations. So it's an incredibly sort of versatile tool. The Schrödinger equation is the partial differential equation, right? But also, sort of describing sort of galaxies through space is a set of ordinary differential equations. So anything that is local, continuous in some sense in time, for instance, and causal is basically described via PDE. So it is the tool for the physicist. What I want to talk about now a little bit is and sort of about PDEs, but also about how we can start to use machine learning to tackle scientific questions. And for that, I want to illustrate. So the way I want to illustrate that is to see how humanity, or has been sort of discovering new scientific laws through the eons. So the first thing is basically to just try things, right? You just you try things, you do experiments, and you figure things out that way. You see regularities and you figure things out. So you build a plane, you fly it. If it crashes, bad luck. Try to improve. So a better way to do things is maybe to first think hard about it and maybe collect data, put things in a wind tunnel, then collect lots and lots of data about the air flows around the wings and such, and then build models based on that, and then sort of have an iterative improvement where you iterate between collecting data, building models, and then building actual real physical objects which you then again measure. So nowadays you can build airplanes completely in silico. So you would basically simulate absolutely everything. You would even simulate the flow of the wind over the wings. And so you can do both the testing as well as the designing and all these things in a computer. And of course, as you go to the right, more and more compute power is needed. But we do have sort of more and more compute power, so that's good. And so something similar you can think about for molecules. So in the old days, people just threw together a whole bunch of things and then see what comes out. Sort of later, people started to do experiments and do sort of careful measurements about everything that they saw, and then build models based on that, and then iterate that. And nowadays, we're trying to see if we can do everything completely in silico. So we actually also try to simulate the laws of physics in our computer, and that's new. So the data is not coming from the world; the data is now coming out of our computers, and we call that sort of the fifth paradigm in some sense. So the core idea behind that is, so let's say, as an example, I want to analyze this car. So I'm a car manufacturer and I should build a cool new car. And now I want to figure out how does it work, right? So I can start test driving it, putting all sorts of sensors on it and collect data. But I do know how the laws of physics work. And so I do know hydrodynamics and all these kinds of things. So I can actually figure out, how air flows around this car. And then that generates data in my computer. I mean, it's expensive to do these calculations, so I should not really throw away that data. I should keep it around, and so store it in a big database, recycle it, and then train a model that would next time do this expensive simulation much faster using a deep neural network. So there's a fast route that starts to improve itself the more data we collect on this slow route. And so this is a virtuous cycle where the more simulations we do, the better our models become. Now, a key aspect of this is generalization, just like in any machine learning method, I would argue. Here, generalization is also key because you need to decide when should I go back to my simulator and when can I use my emulator. Now, numerical solvers, they basically really try to solve the equations of physics, and so they generalize very well. Now, an emulator is trained on the data that it has seen, and so it might actually fail if you get outside of the domain where it has seen the data. And so what you really want is sort of maybe an indicator that tells you, how well do you think the emulator would do. And so uncertainty quantification is absolutely key in order to make sure that you only use the emulator model, the deep learning model, when it is possible. Now, PDEs, as I said, are used absolutely everywhere. I already argued this, so I'll just continue. So what is a PDE in slightly more detail? I'm not sure how math savvy people are in this audience, but there's not too many equations, but this is one. So there is a bunch of fields U. So these are, let's say, 10 fields. You can think of wind velocity and pressure and temperature and all these things. They're a function of both space and time. And I'm going to take I'm going to study the change of time of all of these fields by taking the time derivative. And the time derivative of these fields is given by some function of explicitly time and space, the fields at position x and t, but also its spatial derivatives. You could argue, why not have a second order and higher order temporal derivatives? Well, there's a trick in which you can always add more fields and turn it back into a first order equation. So this is the most general thing you can write down. Of course, you have to specify your domains, and you have to specify initial conditions, and you have to specify boundary conditions. Now, for a certain set of initial and boundary conditions, you can prove the solution will be unique. So the trick that we want to start playing with these PDEs is now the one that I just described, but this car. We could just think of this solver as a numerical solver. You can think of that as a differentiable iterative program, right? You iterate, from all the information at this point in time, you try to figure out what the fields are at the next point in time in all of space, and so you iterate this forward. But we can think of that as an iterated map, and so we can backpropagate through it in principle. Now you can also, instead of following exactly the numerical solver, you can sort of relax a little bit, the solver, and sort of start to insert, parameters in places where there weren't any parameters, to see if you can improve this sort of solver based on data. And that's exactly also how this happened in history, and I'll tell you a few examples of that. And so in the further extreme, you just completely, remove all reference to the numerical solver, and you basically just treat it as a deep neural network. That's the other extreme. And of course, the key question again is generalization. If I've trained something like that on a bunch of data, how well does it generalize if I change the initial conditions, or change the boundary conditions, or maybe the geometry, or maybe the parameters of the PDE, or maybe the dimensionality, all these things, how well does it generalize? That's important because if you've already done the numerical simulation, that's a lot of work. So you want to be able to apply your model to new data. So here's maybe one example I want to highlight of sort of one of the first examples of this. So this is a paper from 2019. So you can see it's all quite recent, where people decided to stay very close to the actual numerical solver. The only thing that they basically said is, well, if I have to take these sort of partial spatial derivatives, numerically they're implemented using these kinds of filters here, and so these filters are predefined. People have sort of thought long and hard about what these alphas should be, and then they're used. But they decided to, well, why don't we actually learn these filters, these coefficients alpha, and then just stick them into the regular solvers. And they found that, for instance, if you train them, then some filters close to sort of these shock waves and some of these that can form in some of these PDEs, the system likes to use a different form of these filters than if it's sort of in another regime. So it now becomes an adaptive numerical filter to compute approximately the derivatives that you need in the PDE. Okay, so that's sort of like, okay, let's take some things which are not actually parameters and make them parameters and see if we can learn them. In the other extreme case, there's also a couple of examples. This is also a very interesting one. It's called a physics-informed neural network. So the idea here is that it's what we call an implicit model. So you take x and t, which is so 4 numbers in 3 dimensions, right? So in 3 + 1 dimensions, you now have like 4 numbers here. You stick them in and you push them through a neural network, and that predicts the field variable or all the field variables at that position and time. Now you backpropagate through this neural network to get the derivatives, right? You can get, du dt, du dx, the second order derivatives, etc. You can get all these by backpropagating. And then the PDE is basically a constraint in all these derivatives, right? It's like d dt of u minus d squared dx squared of u equals 0. That's a constraint. And you just say, I want that constraint to hold. And that's your loss function. Now you can also add some supervised, loss function where you sort of actually do numerical integration and you get some actual data from the actual So numerical solver, you can add that, but then you can just do this. In principle, you can do this in unsupervised way. Now, this is a great idea. It works well in high dimensions. In low dimensions, it doesn't seem to beat sort of gridding methods, which are more powerful. And there's the other class of models called neural operator models. Deep O-net and Fourier neural operator are two prime examples of that. There, the idea is to basically have an autoregressive model, which takes a whole bunch of fields, basically solutions of all these fields at all x at a particular time, and train some operator that maps that to all the fields at a later point in time. And then you can sort of iterate that in order to produce all of the sort of solutions of your PDE forward in time. And we've also contributed one paper based on neural message passing and neural PDE solvers that used basically an irregular integration grid, which was represented by a graph neural net, and the integration basically is like sending messages over this graph neural net. Now, I just want to just emphasize that this field is going very fast, right? So I just showed the paper 2019, so maybe 2018, 2019 is when this field started to develop. A bunch of, let's say 2 highlights of how fast things can go. So this is ForecastNet, which is an NVIDIA model that basically is a global model for the entire surface of the Earth that tries to predict tries to predict the weather forward in time. And so here you see sort of the current weather and 2 insets, and here you see the forecast prediction 96 hours in the future, and here you can see the ground truth, which is kind of nice because you always have the ground truth for weather, so you have a lot of supervised data. And you can see that it very nicely predicts, let's say, the location of these storms, for instance. Now, even more recently, I would say a couple of months ago, this paper came out, Pangu weather, which is from Huawei. That was again a huge leap forward relative to ForecastNet. So this actually claims to predict the weather on a 5-day forward pass. So 5-day forward prediction better than the actual numerical integrators, and in the order of 10,000 times faster, right? So here you have it, like 10,000 times faster and better prediction than numerical integrators. Now, and that's in the span of, I don't know, a year, right? So this gives you a sense of how fast this field is evolving, and I predict that next year we'll see a lot of really cool results in this field as well. Okay, so some conclusions for PDEs. Yes, machine learning will start to play an increasingly important role for PDE solving. It's the most important tool for scientists, and we can start to apply machine learning to solve them faster. It can have a huge impact, not just for weather modeling, but like many, many more things. There's also many challenges. Of course, we want error guarantees. Numerical solvers give you error guarantees. Deep learning does not, and so we need to come up with some way of creating that, or at least creating trust, or maybe good flags to tell you when to use it and when not to use it. We need to deal with data sparsity. We need to deal with generalization, stability over long rollouts, multi-scale modeling, like the weather is an inherently multi-scale problem, non-regular grids, non-regular geometries like tokamak, plasma reactors, etc., etc. So yeah, so let me just leave it at that. And so then transition now to molecules. The second half, I'm on half time, so it's good. So the second half, I'm going to talk a little bit about molecules. So a different domain, but still obviously science. And the reason I find molecules fascinating is that everything is made of molecules. Unless you will get exotic. So if you want to, there's 4 forces which may not be so exotic. The gravitational force is not so exotic, and the electromagnetic fields we all know, those are not made of molecules. Then there's 2 nuclear forces which are pretty exotic, and you never, you don't encounter them every day, but they're also clearly not made of molecules or atoms. Of course, if you look at things at very high energy, things start to break. Plasmas, quarks, leptons, clearly that's not molecules, but certainly matter. everything else, you know, is basically made of molecules. So if you control, if you understand, if you can simulate molecules better, you'll be able to do a whole lot of really cool and important things. So he'll just list out a few things which are cool and important. Drug discovery, which is figuring out, you know, or generating or optimizing or designing a little molecule that sticks into some pocket of a protein and sort of makes it dysfunctional. Photovoltaics, like solar cells, which is turn, you know, so the heat or the light from the sun into energy and then store it. Also, you know, depends on molecules and the design of these molecules which sit in these solar cells. 20% of all the energy that we lose as heat is being lost through friction. So if we can build better lubricants, then of course we can reduce the amount of heat that we lose that way. Catalyst design is a huge market, actually. It's a, you know, finding new catalysts for accelerating chemical reactions. For instance, if you want to split water into hydrogen and oxygen, important for the energy transition, it's actually very expensive at this point because you have to go over a high energy, you know, barrier in order to get that reaction. For instance, in electrolysis, and people are actively designing better catalysts to lower that energy barrier and make it cheaper. Another really important one is a fertilizer. How do you generate fertilizer? It's currently done by a very old process called Haber-Bosch, and you know, we need much better catalysts to generate ammonia. And then yeah, of course, also, you know, in biology, even you know, whole cell modeling would be interesting. You know, talking about whole cell modeling, I just want to give you a sense of how incredibly expensive it is to simulate these molecules, proteins, you know, materials in a computer. So there's this competition, or there's a prize, the Gordon Bell Prize, and in 2020 it was for MD simulations. And so here's an MD simulations over 305 million atoms, which is something like a virus. So tiny thing still. It took 27,500 GPUs to run these simulations, and similarly for a tiny little piece of metal, also about 27,000 GPUs. So incredibly expensive, and that's of course still a very approximate calculation. Okay, I see a raised hand now.
Yeah, it's just me. About the previous slide, do you have any idea how much time does it take for those simulations?
Yeah, that's a good question, actually. I don't know precisely. So I've asked myself that question too, but I'll come up with an answer for you. I would argue weeks, but I don't know precisely. But yeah.
Okay, thank you.
Yeah. So then why is it so expensive to simulate molecules? So this is really getting at the crux of the problem, right? So why is it so expensive to simulate molecules? There's two reasons why it's really expensive. The first one is basically, you know, in order to, okay, so let's first see what we need to do, right? So we have a bunch of atoms. They're connected through the sort of forces or bonds. And in order to move the molecule forward, let's say wiggle it forward in time to solve the ODE, the ODE is just Newtonian mechanics. So that's 17th century sort of physics, very old physics. So okay, so we can write down the sort of Newtonian mechanics equations, that's fine. But then in order to compute the force, that force has to be computed through quantum mechanics. So for every tiny little step of moving, you know, a femtosecond into the future, for every atom in your molecule, and you might have a billion of those for a small piece of material, you have to compute a full quantum mechanical calculation. It's utterly impossible to do that, right? So I'm always in awe of nature in some sense that it can do these calculations so quickly, right? It's a giant quantum computer that can compute all these things in incredibly high speed in some sense. So I don't know, it's just fascinating that nature can compute these things so quickly forward in time, if you think of nature as a big computer. So that's the first thing. But then the second thing is that even if you would, let's say, have these forces given to you by an oracle, you would still have to battle sort of a very nonlinear dynamical system, which is actually a very chaotic system, which means that if you would start the system at a tiny sort of different initial condition, it might end up in a very different state later down the road. So there's also that which makes, you know, the actual sort of dynamics of molecules very hard. And so you really have to think of this as statistical averages, right? You have to think of that as, you know, more computing sort of average quantities rather than the precise individual location, because that's utterly impossible. So again, here we can make progress, and I'll talk about two ways to make progress using machine learning and this fifth paradigm thinking. The first thing is, okay, so let's do a whole bunch of calculations using quantum mechanics, let's say DFT calculations, which is an approximation to quantum mechanics, to compute these forces on a small set of molecules. Now, instead of throwing away that data, we're going to store it, you know, in a neural network, in the weights of a neural network. And then next time around, when I see something that is similar, instead of running the quantum mechanical simulator, I will then actually use my neural network to predict the forces. Now, that thing is called a force field. And chemists have been working on that already for quite a few years. And they're very well advanced now, to the point that you can really use these force field methods to accelerate your MD simulator many orders of magnitude. So that's real progress, right? So that's where we now shortcut, we sidestep the quantum mechanical calculation. You know, we could also try to think about if we can actually shortcut quantum mechanics itself, or, you know, people have invented all sorts of interesting approximations to the full quantum mechanical problem, which scales exponentially in the number of electrons. So you can only do, you know, very accurate calculations with a handful of electrons. But typically, you know, there's thousands or millions of these electrons around, right? So how do you then approximate that? But there's a very interesting, you know, if you haven't seen these kind of quantum mechanical things, you will not learn anything here. But if you have, then you probably also don't learn very much. But I'll just show you this anyway, which is, you know, the most important thing is that if you try to solve quantum mechanics on n electrons, you have to solve a partial differential equation in 3 times n dimensions, very, very high dimensional. So what people have done is they said, well, let's map that back down to a 3-dimensional equation. By basically, instead of trying to trace every electron separately, we're going to look at the density of electrons in a piece of space. Like if you look at the density, then it becomes 3-dimensional. Okay, people can do that, but then unfortunately, you know, you have to write down some energy of that density, and you don't know what it is. And so here's a real opportunity to learn that from data. And Deepmind, in fact, did something like that, and it's called DM21. But even before that, many papers were there that were also trying to improve these functionals as a function of the density. Because once you have this functional, then suddenly you can run these DFT calculations much better. I just want to show you this this demo, which comes from a Quanta magazine. I just think this is incredibly cool, because when I look at these things, I get a much better feeling of what's going on. So these okay, it left me. So these green blobs are basically the electron density as it is sort of moving through time, right, and space. And you can sort of see how it sort of, you know, sort of repels itself, but sticks to the atoms around it, right? And it's that movement that you're trying to approximate using DFT. Okay, so basically what we really want is to build a search engine for these molecules, right? So the holy grail is something like, okay, now I have these simulators, for instance, for, you know, molecular dynamics. I can do them fast using my emulator, my neural network. Maybe I can even do my quantum mechanics fast. So I can either do the simulator, or I can do the fast neural network to compute all the properties of my molecules. And then I want to search in this space, which could be something like, you know, try something, you know, predict the properties, and then do some kind of Bayesian optimization in order to, you know, to walk through this space of molecules to find the molecule that you really want. There's also something which is much, much cooler, but also harder, which is inverse design, where you just give me the properties and it will generate, like an image with the prompt, it will just generate that molecule for you. Now, I think that's the holy grail, but obviously, you know, there's nothing for nothing. The sun only rises for nothing. This is a very hard problem. Okay, so I just first want to quickly go over what the search would look like. So the search is basically, you know, I have a whole bunch of things that I can do in order to analyze my molecular compound. For instance, I could have a very fast machine learning layer, which force fields, which very quickly compute things. I can have a computational chemistry layer, which uses, you know, density functional theory, and it's expensive, but it's still in your computer. And I can have like a sort of maybe a sort of a completely robotized automated factory, which does, you know, thousands of experiments in parallel, which you can sort of ask, which you can steer with my machine learning algorithm. And then I need some kind of agent. And the agent is going to reason about, okay, at this point, how much accuracy do I need? How much budget do I have? So which one of these layers am I going to call in order to get more information about, you know, my search or about the molecules that I need, right? So it could be like, and I want to look at these molecules, and I'm going to stick these molecules in this layer, but some other molecules which I have maybe already ranked very highly, I might just throw, you know, I might just hand over to the factory and sort of start producing them and testing them in a real sort of lab. And every time I do these things, they produce data of various accuracy and fidelity, and which I can then use to improve my machine learning layer, right? And that's a virtuous cycle that should improve itself. Now, the cooler thing, as I said, is this where you can actually generate molecules out of thin air, like images with a prompt. This is work, you know, I did with these brilliant students here, Victor, Garcia, and Emil. I won't go into too many details. The trick is to use, and that's I think the fascinating part. You just use exactly the same diffusion-like models that people use for images, but now for molecules. Of course, you know, a molecule is the perfect thing to make equivariant, since if I rotate it, the property shouldn't change. So it's an equivariant diffusion-based molecule for molecular generation. By the way, here is also Clément Vignac was also involved in this paper. The whole thing was equivariant, and we can now generate these molecules, and it works beautifully. They are in fact, you know, stable molecules that could exist in the world. We haven't really thought how easy they are to synthesize, but they're thermodynamically stable at least. And then, you know, the holy grail is to condition this on properties, right? And that's the hard part, right? Because once you can do it, you can say, okay, give me a drug with, you know, with these particular properties, or give me a material with these particular properties. For instance, that it catalyzes something, or it binds to CO2 or something like that. Now that's something that that isn't quite yet matured, but we've started to do that. And Joshua Benjo raised his hand.
So why do you say that it's difficult? I mean, if you do generative models, you can do conditional generative models. You can train on pairs of you know, the molecule and the properties. So why is it fundamentally more difficult?
Well, I think there's a lot of properties, right? So it depends a lot on the properties that you want to condition on. So one of the reasons I say it is because we've tried it for, let's say, polarization, and it didn't work all that well. That doesn't mean it's fundamentally difficult. The other reason I'm saying that is, if you know, there's a huge number of properties, including lots of combinations of properties that it will be able to have to generate, right? So generating from a equilibrium distribution is one thing, and you need a lot of data to be able to do that. Now, if I want to generate lots of molecules from an arbitrary set of conditionings and find viable molecules, that feels like a much harder map, because you have to know conditional things and then, you know, predict that the distribution for which is different for each one of these conditions. That seems hard, but maybe we will solve it. I don't know. At this point, I don't think we have solved it, because if you have solved it, you know, you have a very powerful tool in your hand, right? Because now you can say, okay, I want, you know, a drug molecule with all of these properties just generated for me, and if it is be able to do this with that would really change the world, in my opinion.
So I remember the days when our early generative models of images
Yeah.
didn't quite work when you did conditional generation, except maybe for like object category. And we've made a lot of progress, as you know, DALL-E and so on.
Yeah.
So, but the technology didn't change that much. Mostly it was like larger models and larger data sets in this case. I'm not saying this is always the answer, but maybe it's not as difficult as we think.
No, I agree. I would really love to be surprised again, like with these other, I didn't predict, that things like this image generation could work so well. So I really hope that in 5 years or so, this does work very well. But I do think if it worked very well, we really have something very, very powerful in our hands now, right? Because then we can really generate materials and drugs on demand. I mean, it's just hard to imagine what that would mean, actually. If you can just specify a bunch of properties and then it would just generate molecules with that particular property.
One option is that we do something that's a little bit like Monte Carlo tree search, in the sense that at the time when you request for these conditions, you can sort of fine-tune the model so that it works well around that part of the space by querying the simulator or something that contains the energy function or whatever that tells you how good the match is.
Yeah, so definitely, you can do things like you would generate things, and then you might sort of drive, let's say, the sampler in a certain regime, collect more data there, retrain your model. All
or
these things
fine tune or whatever.
Yeah.
Condition, fine tune, whatever it is.
And for certain conditions, this would certainly work, right? But for the combinatorial large set of all conditions, that might be, a big thing to ask. But then, I'm happy to be surprised, because maybe it does work. And I think we should go for it, right? That's the thing. This is the thing to figure out in the next 5 years, in my opinion.
Thanks.
Yeah. So quickly. So one of the work that we did was with this group of people at EPFL, and I think you have seen actually a talk by Ilya about this sort of a linker design, which is a form of conditional generation where you condition on a set of pocket atoms as well as some fragments that you want in your molecule, and then you generate the rest of it. And that works fine. It's an easy sort of, I guess, way to conditional things. The other thing is what we're working on also at Microsoft Research is this pipeline for generating materials, where you would just state the properties that you would wish, and then you would first have a generative model to produce lots of candidates, and then start to fine tune on these candidates in order to find the ones that have the right properties. Yeah, I'll just skip that because I'm running out of time, and Ilya had already talked about that. I'll just say a few more words about this project and transition path sampling. So here the problem is I want basically to fast track a molecule as it makes it a sort of as it undergoes a reaction or a conformation change, as it maybe folds or something like that. So if you do a reaction, you often have to go over an energy barrier, and if you wait just by doing normal molecular dynamics simulations, you wait forever, and so you have to sort of help it a little bit and push it along over the barrier. So that's what we've been doing with this particular problem, which is applying forces on each one of the atoms and learning them in a sort of reinforcement learning way to make sure that we can push the molecule over the energy barrier into sort of the next sort of local minimum of the free energy surface. You can make this, you can do this. The math is quite beautiful. That's called a path integral control, but you could do it with any other control mechanism as well. So without going into many more details, I'll just show you a bunch of cool videos here or illustrations where this is the free energy surface. These are the two angles that we're trying to track, and we are pushing the molecule over the energy barrier from one local minimum into another local minimum, which represents another conformer state of the molecule. So here's the next one, a slightly bigger molecule. We've actually recently improved this model by adding a sort of friction term. Turns out to work a lot better that way still, but still quite a bit in progress, but it feels like a very promising technology. And then here's yet a bigger one, which is folding itself up under the forces that we apply. Okay, so as I already sort of discussed briefly with Joshua, so I feel this represents an absolutely huge opportunity, which is why I'm so excited about it. We've talked about PDEs and the enormous impact that can have, because it's basically the tool that's being used across all of the sciences. But molecules, if we manage to control molecules and sort of design molecules at will, we can basically design any material that we want. And just to sort of slightly dramatically sort of state that how important materials have been for humanity is that we've named sort of the eons in which we live after the materials that we use, right? So Stone Age and Bronze Age and Iron Age, now we are Steel Age or Plastic Age or whatever, right? But what if you can just create any material on demand, right? You just type in your phone, I want a material with these properties, right? And then a drone comes in and brings you the material. It's just hard to imagine what that would actually, what you can do once you have that sort of technology in your hands. So there's many ways why you should be working on this, because it's the sciences itself, physics and chemistry and biology, have really developed into very mature fields. But now we also have the computational sciences, which are sort of combining themselves with these sciences, like simulation science and machine learning, and in the future quantum computing. And then perhaps most importantly is the applications, which are becoming increasingly important in health, fighting pandemics, resistant bacteria, etc. The energy transition, more important than ever with the war on the east of Europe. We need to accelerate the energy transition. And sustainability, we have to pull out the carbon and make sure that the climate doesn't change so dramatically that the Earth becomes unlivable, right? And so the first question, will machine learning change the way we do science? Yes, absolutely. I think it's the next frontier for machine learning to disrupt. I also think there's absolutely huge opportunities for societal impact, both in health and sustainability. And if that's not enough, I personally think the future economies will center around pharma, catalysis, and materials, and climate change, right? So if you want one point of evidence, maybe, is that a couple of days ago the EU strikes a deal to boost the carbon market, basically by starting to tax carbon emissions and introducing a sort of a trading market on carbon, right? So trading rights for carbon. Now, if you can have a new way to pull out lots of carbon out of the air, you can become very rich, because you can basically sell those rights to other industries who wants to emit those carbon rights. So you can see how an economy might actually develop around basically a climate. And so you can work on this out of idealism, but you can also work on this because there's actually economic opportunity there. Or you can work on this because it's just plainly super exciting to work on scientific problems. And I'll stop there and wait for questions.
Thank you so much, Prof. Wallin, for the great talk. Jonathan, do you want to go for the first?
Oh yeah, sure. Thanks. Yeah, thanks again for a wonderful talk, and thanks M2D2 for this season. It's been a lot of fun. Really great way to spend a Tuesday morning for me. So it seems like all of these advances in deep learning we've had over the last decade and a half plus have come from a combination of either sort of better, newer architectures, more computation, or better and more data. And with some of these chat GPTs and sort of image generation, as humans, naturally we're generating a lot of this data, and you can pay somebody a penny an image to label these things. But especially when it comes to drug discovery, public data sets are small and oftentimes very wrong. And even personal data sets. I can pay somebody to synthesize these molecules. Error rates are high. Sometimes you get data you can't even interpret. It's not good, it's not bad, it's just, I don't even know, there was some error in this. And I wonder, what are your thoughts on if we may end up hitting sort of practical limitations of how much data we can get? It seems like the architectures, these group equivariant graph networks are, they're beautiful, they're fantastic, they make sense. We're improving upon efficiency and things like that, but fundamentally that architecture seems to be the sort of right architecture for molecules. But we're getting maybe tens of thousands of known, crystallized binding, bound structures. Can we get over that hump in the next couple of decades?
Yeah, I think it's an excellent question. So the fields, so to say, language and image and science are actually different in some ways. So the one that you alluded to is that there is lots and lots of data on the internet for the domain of images and language, where there might not be as much data like that in sort of molecule space, materials, catalysts and stuff like that. So it means that perhaps the art of modeling is still somewhat more important. So it's some of the, in some sense, it's a little disappointing that scaling is all you need in some of these fields, right? So making your models bigger and bigger and let it eat more data, and it will do amazing things. So transformers will basically do everything you want. In a way, for somebody who likes modeling, that's a bit, you basically need engineers to do that rather than scientists or modelers to do that. So perhaps in this field, it's the balance is struck a little differently, in the sense that there's naturally less data, and we need more inductive biases injected in these models. Like symmetries are one of them, but for instance, you can think for quantum mechanics, there's lots of boundary conditions and limits that you can all build into these models, and that will certainly improve these models. But even there, it's kind of interesting. So there's first of all, the data will only increase, and the good thing is that we do know the laws of physics, which is really different from internet or language. We don't know the actual fundamental laws of language. We have a lot of data about it, but and we have some guesses how language works, but it's not as crisp as quantum mechanics, which is correct like 10 orders of magnitude behind a comma or something like that, right? So every time we generate data, it's kind of worth a lot. It will just stay around, and this amount of data will start to increase over time. In fact, if you imagine a search engine where people constantly interact with an engine to do computations, and you store all that data, that database might actually grow pretty fast. And I don't have a good estimate of how much you need in order to saturate, basically. At some point you might just have enough. And the good thing, for instance, about some of these models is that they are universal. So in quantum mechanics, if you try to approximate this free energy functional that you need in order to do DFT, it's a property of an electron soup. Once you know that, you have it, right? It's not like you need to start over again for the next molecule. So it generalizes. In principle, it could generalize very nicely. So I have good hope that it's clearly a balance between these two things, like modeling and inductive biases and generating data. We are, one of the core things that we start doing in AI4Science is generating data. These databases expand pretty quickly. I mean, like in the materials project, I think they have like a couple of 100,000 materials already, and they computed all the DFT calculations for that. And so these databases are expanding very quickly. And so I think we'll see sort of a slow movement from first the models with lots of inductive bias, and then slowly more and more sort of data is going to take over and the models get more data driven.
Yeah, thank you very much.
Question from Zachary in the chat. How do we condition molecular generation on binding to a specific target protein? I would assume there's a little to no data for target where there aren't existing therapeutics.
How should there's targets from the existing tools? I'm not quite sure I completely understand it, but so what we did was basically you can condition on the shape of the protein that you want to sort of neutralize, right? So if you want to find, let's say, a particular small molecule ligand that fits into the pocket of some other, of some protein, then you can train, you can train a model to do that on many different pockets, right? So you can just have one model that should be able to conditionally generate given a pocket. And so you can amortize in some sense across all these different, or generalize across all these different sort of three-dimensional structures. And then if you have a new pocket, you just fixate that particular pocket and you generate molecules into it. So that's as far as my knowledge about that goes, but maybe the person can unmute and maybe explain more. Is that possible? Or?
No, I think you answered what I was asking about. Just like if we have a specific target, but it seems like you're saying that we would have to learn how to predict affinity for the target instead of having target specific data, which makes sense to me.
Yeah, so I don't think we need target specific data. I think we need a model that is being trained on many sort of different pockets and and many different sort of molecules which stick into those pockets. And then once we have that model, we should be able to generalize to new proteins in new types of pockets. So it's one model that would generalize across different proteins in different pockets. That's the idea of conditioning in some sense, right? That you don't have to train a new model for every new sort of thing you want to condition on. You have one model and there's an input parameter, which is the shape of your pocket or your protein or whatever. And then if you set that parameter in different ways, the model should still be able to generate sensible molecules. That's also maybe, is the discussion I had with Joshua, which is why I sort of feel it could be difficult, because you want one model, but there's many different ways in which you can condition it. And it's a very high dimensional set of things that you can condition on in a very, it's a combinatorial space of things that you want to condition on. And every condition, it has a different distribution. And so somehow with one model, you have to capture all of these distributions under all of these different conditions. Feels like very difficult. But then again, generating faces also feels very difficult. So.
Perfect. Lance?
Hi, Professor Welling. Thanks for the great talk. So I'm working specifically for drug discovery, so I have a question for that. So I can see that we can use machine learning to help find like heat molecules. But like as you may know, like many failures happens when the molecule actually get tested in cells. Yeah. I don't know, in such a complicated system, can machine learning help in any ways? Because like for MD simulation, they can only model like a very small system.
Yeah, so I think there's two failure cases, I guess. I mean, again, I'm not a biologist, so I just parrot what I hear other people say, right? Without much, like a good chat GPT, I'll just parrot what other people say. So there's two failure cases, right? One is basically that the model isn't good enough, so your clean sort of, in silico setup isn't good enough for the real world, and it doesn't actually bind. So I think that could probably be improved. I think that's just the technology that has to improve and become more realistic. I've heard that the more complicated thing is that you not just want it to bind to, to that molecule. You also want to make sure it doesn't bind to many other, proteins which are in your body, which are really important, and you don't want to neutralize them. And so the more complex the organism becomes, the more of these sort of constraints there are, right? It can't bind to this, can't bind to this, can't bind to this, right? And so now the set of conditions starts to grow very, very large, right? You have to bind to this, but you cannot bind to this and this and this and this and this and this, and this, right? So there you can see this how hard this could potentially become. I don't have a good sense of so the way I view this is a tool that's not like a magic, a magic sort of system where you press a button and then something comes out and then that's it, right? It's more like a tool that works with the pharmaceutical, with the what is the pharmacologist or whatever you call it. So right, you generate things, and then they look at things and they study it, and then they may go back to the tool and they change something, and then they generate new things, and then they look at that, and if they're sufficiently convinced that it's not a toxic thing because they have their own intuitions about that, then they might go to the next phase. So I view this for a long time. It's probably going to be just an interactive tool, but that's also the good thing, right? Because if it would only be useful when it would be perfect, right, it would be very hard to develop it because it might take 10 years to develop. So if it's going to be useful on the way to becoming perfect, then there is a clear path to sort of commercialization and being useful all the way, and then the investments will keep flowing. So that's also, what we should aim for in some sense, to make it an interactive tool.
Gotcha. Thank you.
Jonathan?
Yeah, thanks. I'm going to take full advantage of being able to ask you questions, and I recommend everyone else does too while we're all here. So with generative modeling, right, for images, speech, with minor errors in that are sort of acceptable, right? There's all sorts of things you can find, on Twitter and Reddit of, oh, look at the hand, look at the hair, that kind of stuff. With molecules, right, something that's even slightly off is either, like you mentioned, maybe not synthesizable, or completely unphysical. And so it seems like some of the more recent methods, like for example, DiffDoc, a lot of these things, they start with generated conformers from heuristically designed, things like RDKit, and that's been very successful. And so I wonder if fundamentally these generative models that we're doing, I know this sounds like the answer is, well, we'll get there, but is there something where with molecules, we will never have that tolerance for error like we do for images and for speech and for text?
Yeah, so I don't think we have the tolerance, but actually, so the thing is that, so the way these software pipelines work is certainly not, run a generative model and then whatever comes out should be perfect, right? So something comes out, and then the next phase is, run molecular dynamics to relax it into the ground state, first using force fields and maybe then using full quantum mechanical DFT calculations or something like that, until at the very end you're very certain that this is an actual physical molecule that satisfies, it's thermodynamically stable and satisfies all the properties of an actual molecule. Of course, you might not, you haven't thought about synthesis then, but then there's also computer programs that think about, how synthesizable certain things, and you might actually direct your sampler in part of a space where things are synthesizable, right? So you might have an oracle neural net that tells you properties about your molecule and says, well, you're generating things here in this space that are not synthesizable at all. So just get out of this, this particular space, part of molecule space, and sort of move more into that direction. And so you can also do directed generation in a way where, either the human tells you, don't generate here, or the oracle tells you don't generate here, you should start generating in this place, and then this, you condition on that sort of new piece of information, and then the algorithm starts generating there. So it's interactive, and it's not only interactive with humans but also interactive with analysis tools. So a generative tool can interact with an analysis tool, which you could call an oracle, to predict the actual properties that you stuck into the generation process as a condition in the first place.
I just want to highlight the last thing Max said about interactive. You can generate not just one candidate, but a bag of candidates, and then you can use all kinds of more or less expensive oracles to find out, how good they are, and then cycle back into the learner, kind of active learning loop. So it's not just like you have to find the right thing right away. You can iterate through all these evaluation metrics that you may have that may be more or less expensive, from in silico to actual experiments.
Yeah, and so the way I view it is basically, so this picture I had with this Bayesian optimization, loop, right? So you run through a Bayesian optimization loop, which could be an optimization, or could be a sampling loop, right? And it's only part of that is where the generative model sits, right? So it's one piece that basically helps you generate candidates in a particular part of space, but you should be able to direct it in, in certain directions. But it's very interesting to think this through, this particular, this particular process of how we would, go through, designing a new molecule.
I'll just take one last question if you still have time, Prof. Masolin.
I have time, yeah.
Okay, Zach.
Hey, yeah. Thanks for taking my question. I was just wondering what you thought were the most promising methods for uncertainty quantification. There have been a lot of methods proposed, and there's a lot of obvious things to try, like mean invariance prediction, but also conformal prediction is interesting as well. Yeah, so I was wondering what specifically you thought was most promising.
Right. So I think it's a really good question. So if I would have to bet my money on something, I mean, if I'm not betting my money on something, I would say Bayesian, because it's like very elegant. Now, if I would have to bet my money on it, I would do an ensemble. So that's my very honest opinion about that. So Bayesian is really cool. It's very principled. And so that would be fantastic if it works well. But I think ensembles, practically speaking, are actually super practical, and they do work very well too.
Can I follow up with what your thoughts on conformal prediction are for these sorts of problems? Sorry,
what was that? Conformal predictions?
Yeah, conformal prediction.
I actually don't know what that is. Can you explain?
Okay. Yeah, it's a framework that allows you to guarantee that the probability of not including the true prediction in your what's called a coverage set, so you'll have a bunch of predictions, is you get to control the probability of not including your true prediction to be below or above some certain level.
That sounds interesting.
Kind of like a calibration method. It's yeah.
Yeah, so sounds very interesting. I should read up on that actually. Yeah, there's another thing that we tried, which actually also turns out to work very well, is you train one model to predict and then train a separate model to predict the error. So because the first model predicts the value, and then once you have the value on your training set, you have an error, and then you have a separate model, and it's important it's separate because you don't want it to be the same trunk as the first model because of regularization issues. And then you train your second model as an error predictor, and you run both of these models sort of in conjunction. That's another thing that could work. But anyway, yeah, there's many things that we can do, I guess. But I'll read up on conformal prediction.
Does Prof. Joshua has any thought on this question?
Yeah, I wrote in the chat +1 Bayesian amortized, because I think, yes, today I would use a deep ensemble if I had to use one, but I mean to use uncertainty estimation, but they have lots of limitations, right? You can only get so many modes. You don't cover the volume around each mode. And I think that people will be building neural nets that can handle potentially combinatorial sets of modes through the amortization magic.